Today we are graphing rational functions. A rational function will have a fraction bar, the numerator will be a polynomial expression, and the denominator will also be a polynomial expression. Just like before, the vertical asymptotes will always be the zeros of the denominator, keeping in mind dividing by zero is undefined, so that's where our vertical asymptotes will be. For our horizontal asymptote, however, it comes down to comparing the degree of our numerator to the degree of the denominator. So there are three ways that they can be compared. It could be less than, it could be equal to, or it could be greater than. And each of those has a different outcome for a horizontal asymptote. So first, if the degree of our numerator is greater than the degree of the denominator, there is no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0. And lastly, if the degree of the numerator is equal to the degree of the denominator, then our horizontal asymptote will be y equals leading coefficient of numerator over leading coefficient of denominator. So when we take a look at example 1, our numerator is x cubed, our denominator is x plus 2/3. So our degree, if the numerator is 3, degree of the denominator is 1. So the degree of our numerator is greater than the degree of our denominator. Therefore, there is no horizontal asymptote. The vertical asymptote will be the 0 of the denominator, so which would be negative 2/3. So I'm going to go ahead and draw my vertical asymptote at x equals negative 2/3. And then I would use my graphing calculator to create a table of values. First, we can find the zeros, the 0 of the numerator. If you set x cubed equal to 0, you would get x equals 0. So the point 0, 0 is on our graph. And then we'll find other points as well. And then we will plot them. You're going to want to look at it on your graphing calculator to understand the end behavior. So your vertical asymptote, remember your graph, it kind of divides it into two separate curves, and your graph will get closer and closer to that line but won't cross that line. Example 2. Young's rule can be used to estimate the dosage of medicine to give a child if you know the adult dosage of the same medicine. Young's rule can be written as y equals ax over x plus 12, where a is the adult dosage in milligrams and x is the age of the child in years. So to graph this function, we have y equals 200x over x plus 12. The numerator and the denominator are same degrees, x to the first, x to the first. So our horizontal asymptote will be leading coefficient of numerator over leading coefficient of denominator, which would be y equals 200. Our vertical asymptote will be the 0 of the denominator, which would be negative 12. So I'm going to go ahead and, I'm going to graph those in a minute here. And then finding our x-intercept, which would be the 0 of the numerator, and which would be 0. So we'll plot that point. Here's our horizontal asymptote at y equals 200, our vertical asymptote at x equals negative 12, and then when we plot points from the graph, here's our graph. Example 3. Consider g of x equals x minus 2 over 2x plus 2. Graph g of x. So first we're going to find the zeros. So the numerator, if setting that equal to 0, we get x equals 2. So 2, 0 would be a point on the graph. And then our vertical asymptote will be the 0 of the denominator. So when I set 2x plus 2 equal to 0 and solve, I get x equals negative 1. They are the same degree, so our horizontal asymptote is going to be 1 over 2, leading coefficient over leading coefficient. So here's our vertical asymptote at x equals negative 1, horizontal asymptote at y equals 1/2. It has the point 2, 0, 0, negative 1. Part B, which function has a greater y-intercept? So this one crosses the y-axis at -1. This one crosses at -2. So -1 is greater than -2. So g of x has the greater y-intercept. To compare, oh, I guess we skipped the part of comparing their asymptotes. All right. For vertical and horizontal asymptotes, f of x has at most one horizontal asymptote. If the degree of a of x is greater than the degree of b of x, there is no horizontal asymptote. If the degree of a of x is less than the degree of b of x, the horizontal asymptote is y equals 0. If the degrees are equal, it's leading coefficient over leading coefficient. Oblique asymptotes, if f of x, if we've got a polynomial divided by a polynomial, if the degree of the numerator is exactly 1 more than the degree of the denominator, then there will be an oblique asymptote, so like a diagonal line, and the equation of that asymptote will be when we divide, the answer to dividing with no remainder. So we divide them and then we ignore the remainder. And then a point of discontinuity, if we factor both numerator and denominator and they have a common factor, if x minus c is a factor for both, then there is a point discontinuity. It's like a hole in the graph at that point. So looking at example 4, first to find the zeros, we're going to find the zeros of the numerator, set that equal to 0, and then to factor that, factors of 1 that add up to 2 are 1 and 1. So it factors into x plus 1, or, and then set each factor equal to 0, and we get x equals -1. So that will be a 0. Then to find our asymptotes, so for our vertical asymptote, it's always the 0 of the denominator, so that'd be at x equals -4. I'm drawing that here. And then for the horizontal asymptote, there is no horizontal asymptote because the degree 2 is greater than degree 1, but it's exactly 1 more. So we are going to divide them with polynomial long division. So remember, we take the first term divided by the first term. X squared divided by x would be x. Then I take x times x plus 4, which gives us x squared plus 4x. And then we subtract. X squareds would subtract out. 2x minus 4x is -2x. And then we repeat that process. So I'm going to take -2x divided by x, which gives us -2, multiply -2 times x plus 4, and then when we subtract, our remainder is +9. So we ignore the remainder here, and the oblique asymptote is the line of y equals x minus 2. So the answer to this division problem. So that is a line that starts at -2 and has a slope of 1. So here's my oblique asymptote. And then to graph it, we would need to create a table. So I just use my graphing calculator to make a table, and then I would plot points from that table. And here's what the two curves of our hyperbola would look like. All right, finding the point of discontinuity, we need to first factor both our numerator and denominator. So in the numerator, we have x squared minus 4. That's the difference of squares. That factors into x plus 2, x minus 2. So you see we have a common factor of x plus 2. So our point of discontinuity would be at x equals -2. So when the common factor divides out, we're left with f of x equals x minus 2. Therefore, the graph is the same as the graph of y equals x minus 2, but there will be a hole or point of discontinuity at x equals -2. When I substituted -2 in for x, we'd get 4 minus 4, which would be 0. Divided by 0, it's kind of like undefined. But to graph y equals x minus 2, -2 minus 2 would be -4. So this point right here, -2, -4, is a hole in our graph. And then graphing y equals x minus 2, we start at -2, slope of 1. And this is what the graph would look like. There's like a hole in the graph at x equals -2. Because essentially what happens to the original expression is we end up with 0 divided by 0, which is undefined. Thank you for watching.